Well, what happens next? Well, what if it's an operator? If is operator, the token I'm looking at, what do you do that's special? We just take whatever's on top, make it the left child of the current node, and push the node back on. So this token node will be the root, and it'll make the left child whatever's on top. Node top is whatever's on there. And we're going to make that the left child of the current one, push the token node back on. Okay, and finally, so this is an if statement, else if that, and this last one is if the token is a closed parenthesis. This is a tricky one. This is actually has a while loop inside it. Token is that. So what do? We set the current to be whatever's on top, and we create another one. All right, so what we need to do is, we're actually going to totally ignore this. This is just starting a process. Current is going to be whatever's on top. Top is going to be whatever's on top just below that. So what we're going to do is we're going to say binary node current is stack.pop, binary node top is stack.pop. All right. So what we're going to do is we're going to check to see if we've reached an open parenthesis that matches this closed parenthesis. So while top.getValue .charat 0 is not equal to an open parenthesis, we're basically going to keep doing this over and over again. And what we're going to do is we're going to take whatever current is, this thing here, and make it the right child of what's on top. So top.setRight to be current. And then we're going to alter it such that current equals top, and top is whatever's on top of the stack again. So this is basically continually going to set whatever is on top of the stack to be the right child of the next thing down, and then set that whole thing to be the right child of the next thing down until you find a matching parenthesis, which ends up getting thrown away, by the way. And then finally, when we're all done, push current back on. This last part here. Hooray! Boy, what a mess. How do we even figure this out? So if I run this, I should be able to create an expression tree and assign it to the root. And then the thing that it's asking for, the create expression tree is it's asking for a string. The string I want to grab is whatever's in this text field up here, this T field. tfield.getText. Now, prefix doesn't work because I haven't implemented that, but yours does because you've implemented that, right? So let me try printing out infix just to give you an idea that this is actually working. So if I hit prefix, 3 plus 5 times 2 minus 6 divided by 7. So this is actually working in creating the expression tree. All right. Wow, that was a lot of coding. So your job, make sure prefix and postfix work. Make sure your create expression tree works. And then try it out on a variety of different trees. So let me give you a couple test cases just to make sure that yours is working. So let's see, if we do times minus 1. So that expression tree should be created if I do 1 times 3 minus 7. So that should be the input. Infix doesn't matter for you guys, so prefix, the root happens first, so it's actually going to be minus times 137, because the root happens, left, right, right. Postfix, this is going to be 1, 3 times 7 minus. So it basically does this operator in that order, and then whatever this answer is with the 7, it subtracts it. Let me give you another one. So let's see. Divide plus minus 2, 6, 8, 1. So this expression will be 2 plus 6 divided by 8 minus 1, if we were doing it using what we expect as infix. Prefix will be divide plus 2, 6 minus 8, 1. So it always has the operator and then the two things that happen afterwards. Operator, two things that happen afterwards. This one has to wait till these operators finish. Postfix, it should be 2, 6 plus 8, 1 minus divide. How about that for weirdness? So here's the first term of the divide, here's the second term of the divide. Well, other order. So hopefully that is what you're getting when you do these two. All right, prefix and postfix. We've just done a lot of crazy stuff. We have a data structure called a stack, and another data structure called a binary tree. We have recursion, which is what this stuff is doing. And we have use a stack to create a tree using this algorithm here. By the way, if you're curious, this is a variant of the shunting yard algorithm by Dijkstra. So this is actually pretty advanced stuff we're doing all in one project. Hopefully that gives you everything you need to walk through it, and you'll be able to change mathematical expressions.